Okay, I'll take that as a yes as well. Okay, so let's get started. So the topic of this presentation is memory disaggregation, which really hasn't happened yet. We have been trying to do this for 30 years, and I think, are now in the cusp of it succeeding. And when I say succeeding, I mean succeeding commercially. And we just heard a talk about direct CXL, which is doing this in academia. But I think really now this is something that's going to take off and be available widely. And I'm going to start with a general discussion of disaggregation of other resources, such as disks and CPU, which have already been successful, and then take the lessons from these other resources and the lessons from history to memory disaggregation so that we can try to predict as much as we can what might happen. And I'm going to start with something really basic here, just to make sure everything is on the same page. And I'm sure this is background for that everyone knows in this workshop, but I just want to make sure that the word disaggregation as I use is well defined and we all agree on what it is for this talk, right? And so the definition that I'm going to use for disaggregation is to move hardware resources to outside the box. And this really refers to a physical concept. It's a physical construction of the system, not a logical definition. And in fact, when you disaggregate the hardware, you typically want the logical or semantics of the system to remain the same, so you don't disaggregate logically speaking. And so that's the first observation. It's really about the physical construction of the system. And the second part of this definition is disaggregation also implies that there's a transformation, that things used to be one way, and now we're going to change it. We're going to move it away from what it was before, right? And notice that this definition doesn't mean that you're moving all of the resource. You can just move part of the resource, and this is shown in this figure here for memory disaggregation. Parts of the memory have been moved outside of the box to box 2, but there's a little bit left in box 1, right? And the new box can also have a whole lot more of the resource than before, and that could make sense so that it can be shared amongst many different boxes, right? So this is very basic, but I just wanted to make sure that we are on the same page here. And disaggregation has been successful so far for several things, and I'm going to give a few examples here and talk about why they were successful and what were the conditions for them to happen. And so if you think about it, when the mainframes started changing to networks of computers or cluster of computers like in the 70s and the 80s, this was really about disaggregating everything, right? So we took this monolith system that had CPU and memory and so forth, and we broke it into smaller boxes. And so we're basically disaggregating everything there. And over time, these clusters of computers like the VAX cluster, right? They were tightly integrated, but over time they become less and less tightly integrated. And after the cluster of computers, we had network of workstations, and eventually we got to the internet, right? And so there was a really long trajectory in disaggregating the mainframe up to what we have today of many different computers that are very loosely connected to each other. And it's a very interesting journey to look at that. And also, another example I'd like to call out, by the way, this happened. Now, the main reason this happened of the disaggregation of the mainframe is, well, two main reasons. But one of the main reasons, the first one was that people wanted to access the mainframe from different locations, and I think that eventually they realized that it's better for things to be in separate physical locations. And so that's when we have the ARPANET, right? And the computers there were accessible in smaller chunks from various different locations. There was also concerns of cost, and in the case of ARPANET, there was questions of national security, of everything being in one place, and you get a nuclear attack of that and so forth. And so there was an accessibility question for the mainframe. There was a cost and capacity question that motivated disaggregation. The second example of successful disaggregation is storage disaggregation, which happened in the 90s. And that is a very interesting example that, it happened mostly because of the need for high availability of the storage system. And so you have a lot of important data on your storage system in a bunch of disks. And then the computer server where the disk is connected crashes, and now all your data is no longer accessible. And this was unfortunate, especially for applications that needed to be highly available. And so what they did first was to have what's called a multi-ported disk, right? So it's a disk that allows you to connect to 2 different servers, and such that if one server goes down, the other server can still access the data on the disk. And you're not trying to access initially the data at the same time. It was just, you fail over to the second server if you have a problem. But eventually they realized that maybe it even makes sense to access at the same time. And so when you have like VAX clusters can access those disks simultaneously. And it started, so these are the multi-ported disks, but that eventually evolved to a storage area networks, which are things that have their own fabric, and that allows the disk to be connected to more than just one host, and also shares the fabric amongst possibly many different disks being connected to many different hosts. And that was the storage area network. And that allowed not just disks, but also, even tape to be accessible, and tape, God forbid, still in use today. Now, eventually, what we see more recently in this history of disaggregation is that the fabric, fiber channel for storage area networks, then converged. And so maybe we don't need 2 set of fabrics, one of them for the network and one of them for the storage. We can just run everything over Ethernet, over the network fabric. And we have things like NVMe over fabric showing up. And so there was a convergence that happened afterwards and more recently, and still that transformation is still going on. And I suspect that memory, and I'll talk about that a little bit later, the memory trajectory will be similar to the story of disks, in the sense that starting with multi-ported and going to the fabric, just a dedicated fabric, and then convergence of the fabric. Okay, and so the need for disaggregation here happened because of the need for high availability of the data, but also more capacity, right? So once you disaggregate, you can put a whole much more storage in the box. Now, next example of disaggregation I have is power and cooling inside a server. And this happened in the 2000s with the introduction of blade servers. And the main motivation for this was to increase the density. If you look inside a server, 20% of the space is taken up by the power supply and by the fans, right? And if we can be today amazed at how much transistors we can put in a very small amount of silicon, like in a CPU, it went from 2,000 transistors in the 70s to today 100 billion transistors, right? And this is what you get in some of the latest chips from Apple, the Apple M1 Ultra with 5 nanometers technology. And so really the chips have been packing so much stuff there, but the power box and the fans really take up a lot of space there. And in the 2000s, there was a concentration and there was an attempt to make things higher density. And so they didn't want to have every server with 2 power boxes and plus fans taking up all that space, and that was also costly. And so what they did back then was to have a single or multiple power supplies and multiple fans being able to serve many different servers, right? And that's what you get in a blade architecture. And so the servers themselves, they take as input DC power, and then the transformation of AC to DC happens in a single location for all these servers. Now, when I say single location, there's of course redundancy. There are multiple power supplies here, but you don't have to have 2 power supplies per server. You can have like 4 or 5 power supplies serving the entire rack, and you can save money there, and you can make things more dense that way as well. And the same for the fan technology. Now, more recently, successful example of disaggregation was GPU disaggregation. And this happens in the mid-2010s. And there, the goal was to improve utilization. So GPU is this really expensive resource. And if you have a large number of servers that need access to a GPU, you would have to connect a GPU per server, and then you may end up buying a lot of GPUs. And so instead, create a GPU pool, and then you allow every server to access the GPU pool. And so the motivation here, GPUs is very expensive, very valuable resource. And so you disaggregate them and improve their utilization. And now in 2020, Now, this commercial success of disaggregation hasn't happened yet, and I'm going to make the case for memory. Now, we see a lot of research going on here, and we just heard a talk about the XCXL as I mentioned, and other attempts to, in the past, the commercial attempts to make memory disaggregation successful, and other research prototypes in the past as well. But I'm going to make the case of why now it's going to be successful. And before I do that, what are the lessons that we can learn from history, right? And so, and there are two lessons that I want to, but before I get to the lessons, let me just mention why disaggregation started. And it was different reasons for different types of resources, but on this slide I show four main reasons. No, need for more capacity, and this was the case of mainframe and storage. The need to lower the cost, so power cooling and GPU by improving utilization, but utilization itself could be a focus of it as well. And also accessibility and availability, like I mentioned, the mainframe, when ARPANET came up, we had various research organizations around the country that wanted access to the mainframe, but it was difficult because mainframe was in one location. And so it's much better to have a bunch of different computers everywhere, disaggregated with everybody being able to access something a little bit smaller, but at least everybody can access that. And so that's the accessibility or availability. And in the case of storage, the same thing, like I said, when server goes down, you want storage, your data is there, and you want to be able to access from other locations. So these are the reasons disaggregation started. And in the case of memory, there's going to be a combination of these reasons that will motivate it. So what are the lessons from this? Like one lesson, the first lesson is that disaggregation has two requisites for it to succeed. So the first requisite, and to succeed commercially, right? The first requisite is that it needs to solve a burning issue. And by burning issue, I mean a real big problem that affects a large fraction of the industry, right? It's not just like a few players or a fraction of the folks, but it really, a lot of people are being affected by this. And also a burning issue is one that the current technology cannot address. Like it really requires a big transformation. And the reason this is a requisite for disaggregation to succeed is because disaggregation really happens and changes a lot of things. And so the industry must overcome a lot of inertia in the hardware in order to accept and to produce disaggregated solutions. And that requires significant investment. And this is true for multiple vendors, not just the vendor that is selling the resource, like not just the disk vendors or the memory vendors or the GPU vendors, but also the servers that are using this, we call this the OEMs. They need to adapt. And also oftentimes the operating systems and the applications need to be changed to use that new hardware. And so it's not just one player that can come and say, yeah, I'm going to disaggregate stuff. All the players need to come together and agree, we're going to disaggregate, it's going to be a standard, and they need to set a standard that everybody thinks is beneficial for them and agree on that. And that's what in part CXL is doing, right, for memory. And so, and that is really difficult to have that alignment across multiple different vendors. And so it needs to really solve a really important issue for it to be successful. The second lesson that we learn, the second requisite for disaggregation to succeed is that you need to have a feasible technology. And oftentimes disaggregation requires it to solve a non-trivial technical problem. And for example, 10 years ago, Intel tried to do memory disaggregation, and they proposed this, and with their basically a new hardware that would be able to disaggregate a lot of different stuff, including memory. But disaggregated memory requires photonics, right? And that was part of their proposal. And photonics really wasn't a feasible technology at the time. And even today, people talk about photonics, and there is some limited success to that, but people don't talk about photonics for connecting memory anymore, right? And so that effort didn't work. There wasn't a feasible technology, even though 10 years ago, there was a compelling reason for it, but the technology wasn't there. Okay, so that was the first lesson that we learned from history about disaggregation that succeeded. There's a second lesson that we can learn, which is once disaggregation happens, it produces a much broader impact than it was anticipated. Much broader impact than what drove it to happen in the first place. And so, and you know, I call this the surprise impact of disaggregation, right? And so mainframe eventually led to ARPANET and the internet, right? And the internet is such a game changer for technology. Storage disaggregation led to a whole industry of storage appliances. And now once you put storage in a box outside, then you can think of that box implementing all kinds of functionality like fault tolerance, point in time snapshots, continuous backup, disaster recovery, virus scanning, and so forth. And that created a whole industry. So the companies that used to be just selling commodity boxes for storage now can sell a appliance that has a lot of added value. And so that was a huge business impact for storage vendors. So power cooling with blade servers led to new data center designs and eventually the Open Compute Project and Open 19, which are basically saying like you're constructing data centers and you're constructing racks, and maybe you shouldn't. There are many things to Open 19 and OCP, but one of the things is power and cooling disaggregation. And so you don't have a power supply or two power supplies per server. You just put this in the rack somewhere and then you use DC power for everything else. And so that took a long time for it. Of course, OCP and Open 19 are very recent efforts. But no, that originated with power and cooling disaggregation and thoughts about how to make racks and data centers more efficient. And GPU disaggregation, the impact is still occurring, but so far we've had things like GPU farms, right? And especially for crypto, though of course crypto has been going on a down trajectory more recently. But no, if you look at the GPU farm, what you have is a bunch of GPU boxes connected to a very cheap CPU, like a $10 CPU, like a Celeron, right? And so you really spend a lot of money on the CPUs, but not on the GPUs, and then you can do all this crypto mining from that. And I expect that the GPU disaggregation will have a much bigger impact in the years to come. It's still too young for its impact to have rolled out. Okay, so this was the part of the talk on the disaggregation of other resources, and now I'm going to talk about memory disaggregation. And meanwhile, let me see if there's any questions. You can post questions on Slack. Let's see. I don't see any questions. So anytime, feel free to post the questions from time to time. I'm just going to stop and see if there's anything you want to ask, and then I'll take it from there. Okay, so memory disaggregation, and this is an old idea. Like I mentioned, 30 years ago, there was these tech reports from University of Washington where they wanted to use the memory of a remote system as a paging device because the network was faster than the disk, right? And so it makes sense for you to swap out your pages, not to disk, but to the memory of another server, and then discuss the issues of what it takes to implement that in a tech report, right? And also, there was, now this one is using memory as a paging device. Direct disaggregation, the first reference that I know of is an ISCA 2009 paper that was done in HP labs. And so, and that's very interesting. That was already like 10 years ago. And that was proposing the concept of being able to do loads and stores to memory, which is outside the box. And then a few years later, the Intel rack scale architecture proposed memory disaggregation as a commercial product. Like I said before, using technologies like photonics, right? And that didn't go much far. And so why then this idea from 30 years ago, why is that going to be successful now, right? And now if you look at the history lessons that I mentioned, there were these two requisites for disaggregation to be successful, and the need to solve a burning issue and the need to have a feasible technology. And I'm going to make the case that these two requisites are now met, right? And I'm going to start with the first one, the need to solve a burning issue. And the burning issue is the memory problem, which I have summarized on this slide as 4 aspects to it, right? The need for memory is growing. The capacity of memory is limited in servers today. It's very hard to propagate memory when you need more of it. And the cost of memory is growing as a macro trend. And so I'm going to zoom in on each one of these 4 topics and explain them in more detail. So the need for memory is growing because big data is moving to memory, and I like to call that now we need big memory for the big data. And so there are, in fact, lots of applications that have traditionally stored data outside of memory and now moving to memory. Like we have things like in-memory databases, for example, is just one example of that. And the reason data is moving to memory is that the more data you have, the faster you need to access the data, because otherwise you're just going to spend your entire time accessing the data, right? And I'm assuming you want to use the data. Now, if you're just keeping your data for archival purposes, then you might as well put it on disk or you put it in cold storage. But if you want to make use of your data, then the more data you have, the faster you need to access it. And also applications just collecting more data, right? There is a sense now that with all this machine learning, that we have all this intelligence that is able to mine data that we have. And so let's just collect everything and keep it so that the machine learning can make use of it. But we also have things like content distribution networks, real-time analytics, time series processing, and so forth. And those things all take up and keep a lot of data. Also, I mentioned that memory have been, and so databases have been moving to memory databases, but this is also true for NoSQL systems. And they need more memory. And now you can think of NoSQL systems, you can scale out, and so you can get more memory by just adding more computers. But the problem, if you try to do that too much, is that your footprint becomes too big. And so you really want to have more memory per server in order to reduce that footprint, right? You don't want to have your scale out solutions with 500 servers, right, in a private data center. You might be happier with just like a rack or two, and so you'd rather to have more memory in a server than having to buy a lot of different servers and having to take up a lot of data center space. So this is the first aspect of it. The need for memory is growing. The second aspect is that the capacity for having memory in a server in a single box is limited, and it's limited by the number of DIMM slots that you can have. And so DIMM slots are the places where you put memory DIMMs, and memory DIMMs are the things that are storing the memory chips. And so there is typically a very small number of DIMM slots in a server, and the number that you see is typically like, it depends on how many memory channels you have. And so typically a CPU will have between 6 and 8 memory channels. And each memory channel, you can have 1, 2, or 3 DIMM slots connected to that, right? So then you can do the calculation. There's limits on the total number of DIMM slots. And that limit is so small that oftentimes people buy more CPUs, not because they want to have more CPUs, but because they want to have more DIMM slots. And there's a limited number of DIMM slots you can connect per CPU. So you just add more CPUs to your system. And that becomes very expensive, right? If you're buying a server with more than 2 CPUs, which is kind of the sweet spot for cost for buying a cost-effective number of CPUs. If you buy a server with 4 or 8 CPUs, it starts to become really expensive, because then you have to buy premium CPUs to do this. And then those cost much more, and the cost is not linear. And so, but why is there a limit on the number of channels per CPU? I mentioned 6 to 8 on which you can put these DIMMs. And the reason is that each channel takes up 100 pins. And so, and you cannot put so many pins on the CPU. And the number of pins have been increasing dramatically. But if you think about 100 pins per channel, then once you get to like 8 channels, that's already 800 pins, a large number of pins, right? And so, and by the way, these days, they're no longer pins. So the pins are actually on the board. The chips, they just have a little surface where the pins that are on the board are attached to. But traditionally, they've been called pins. And so that's the terminology I'm using here. And so you're limited on the number of channels, but you're also limited on how many DIMMs you put per channel. And the reason for this is the physical distance. Like these things cannot be too far from the CPU. And so, and the farther you are, the slower the frequency that you can operate, and the lower the bandwidth you get. And so in fact, the number of DIMMs per channel has been decreasing over time. So I said, 1, 2, or 3 DIMMs per channel, but now, things used to be 3, and we moved to 2, and in the future we expect to move to only 1 DIMM per channel. And when we moved from 3 to 2 DIMMs per channel, we lost like a big 1/3 of our memory. And when we move from 2 DIMMs per channel to 1 DIMM per channel, we're going to lose half of our memory capacity in the server. And the reason this is decreasing is because we want to operate the memory at a higher frequency, because we want to have more bandwidth. But if you want to operate at a higher frequency, we need to have the memory closer to CPU. And then there's only so much space where you can put that memory, right? So there's only one or two DIMMs per channel that can do this. And so there's also a limit on how much memory you can put per DIMM. And so that's the density of memory, which is 256 gigabyte DIMMs. Those are very expensive. 64 and 120 gigabytes per DIMM is the more traditional one. So you can do the calculation, then you take the number of channels per CPU, the number of DIMMs per channel, and the amount of memory per DIMM, and that's the maximum total amount of memory that you can have on your server. And now, why aren't we making memory much more dense than before? Why only 256 gigabytes per DIMM? And the reason for this is that very hard to shrink memory. So we have been doing a very good job at shrinking transistors to make CPUs, and I mentioned 100 billion transistors on the Apple chip, right? But the CPU and the feature sizes of transistors is like 5 nanometers now. But for memory, feature sizes are 10 nanometers, which is what we had like 5 years ago. And this number is not increasing, it's not shrinking anymore. And the reason for this is that DRAM requires a capacitor. It's not just transistor. And we're really bad at making capacitors small, because capacitors, they need to hold a charge. And if you make it smaller, then it has to hold, there's less space to hold charge there. And so, and then becomes a problem with the refresh. And so it's really difficult to make memory more dense and to be able to pack more memory into each chip. And so the totality of this is that we really can't stuff more memory into the servers that we have today. And so the capacity is limited. Now, another aspect of memory is that if you create a server and you buy and you provision memory and you realize that you need more memory in the future, it's very hard for you to upgrade the memory. And so, and there are several aspects to that hardness. But one of them is that, okay, so you have the capacity is limited. So maybe you've taken up all your DIMM slots. If you need more memory, you have to replace current DIMMs with higher density DIMMs, and the cost is much higher, and the cost is not linear. And so you can see this figure here. This is $1 per gigabyte. This number is from about a year and a half ago, but the trends are still the same. And so if you go from 64 gigabyte to 120 gigabyte, you'd expect, okay, so I double my memory, I'm going to pay twice the price. But no, you're going to pay more than twice the price because the $1 per gigabyte has increased, right? And if you go to 256 gigabytes, you pay even more. And so the cost is not linear once you go to higher density. But that's not the only problem of upgrading. So servers have the so-called the memory population rules that say that all the DIMMs that you have in your system must have the same capacity. And so you cannot just change one DIMM in your system, you have to change everything. And so that means that the memory that you currently have, you have to throw away, and then you have to put a new memory, right? And that is really expensive, and that's unintuitive, that you're forgetting memory, you have to throw memory away. And this is a problem that really memory disaggregation solves, right? You don't have to throw your memory away. You just put the memory outside the box and have extra memory. Now, the last aspect of the memory problem is that the cost of memory is growing, and that's a macro trend. And there are two reasons for this. There is conjunctural and structural reasons. Like the conjunctural reasons is that there have been a high demand of memory from new users. Not just servers need memory, but you have like 5G handsets need more memory. You have self-driving cars, and you have gaming consoles. So there are large parts of our technology appliances besides servers that have been asking for more memory. And so the demand for memory has been increasing. So these are conjunctural reasons, but there are also structural reasons that have to do with how the memory industry is organized. Because if you think about it, like memory is supposed to be a commodity, right? If it's a commodity, it's supposed to be really cheap, but it's not really cheap. In fact, if you are going to build a server today with lots of memory, let's say 1.5 terabytes of memory, which is becoming a more common configuration for a server, you're going to spend half of the cost of the server with memory alone. So half of the bill of materials is going to be memory, and then the other half is going to be CPU and everything else that goes into the server. But it's kind of crazy, right? So what's going on? Memory is supposed to be a commodity. And yeah, memory is a commodity, but the industry has consolidated. So if you look at 2007, there used to be 11 DRAM companies around the world with 40 foundries. And these companies were competing and they would go and build more foundries and produce more memory and flood the market, and then they would produce so much memory they don't have to sell memory below cost, and then they would go bankrupt or they would get acquired, right? And so there was intense competition for such a commodity resource, and a lot of companies doing exactly the same thing. And what happened is that the companies learn about this, and now there's only 3 companies that do memory in the world, right? So there's Samsung and there's Hynix and there's Micron, and that's it, right? So high-end memory, there's only 3 of them. And they're very careful about how many foundries that there are. So these are the things that manufacture the memory. How many foundries that they deploy, and they don't want to flood the market because they know that if you invest in a foundry, it's going to cost billions of dollars, and you're committing that before you sell your memory. And then you realize that you have produced more than you have the ability to sell because everybody else is also producing more memory and they have to sell below cost. So they have learned not to play this game anymore. And so nowadays they're much more careful about how much capacity they put into the market. And so, and for that reason, so it's essentially oligopoly now. For that reason, memory is much more expensive. Okay, so that's the burning issue, that memory is problematic. And memory disaggregation solves the problem. Well, it doesn't solve the problem that the need is growing and the need is going to continue to grow, but it solves the other problem. The capacity now, once you disaggregate, you can put the memory outside the box and you can have more room there to put your memory. Upgrade becomes, of course, very easy because you can put that memory outside and you can add more components outside the box. And by doing that, you upgrade your system with more memory. And the cost gets better as well, lower cost. And the reason, it's not because the cost of disaggregated memory is going to be smaller. In fact, people are expecting to have a premium for that memory, which is sitting outside. So it's probably going to be more expensive than the memory that sits inside the server. Even because you have to pay for the memory controller, the special CXL stuff, and the fabric and everything. So probably the cost per gigabyte outside, for memory outside, is going to be higher. But the way that we solve or we help the cost problem is we improve the utilization, right? And this is a well-known benefit of disaggregation, that once you put the resource in a pool and everybody can access the pool, you don't need to buy as much of the resource. You can put less stuff in the pool than you would have put separately, right? And so because the pool, you don't have to provision each one of your servers for the worst case, you provision the pool for the worst case, and then it so happens that the worst case for all the servers don't happen at the same time, and so therefore the amount of memory you can put in the pool is lesser, and the memory that you do put in the pool is better utilized, and so the cost becomes lower that way. So memory disaggregation is going to solve the problem, but that was not the only requisite for you to be successful and for the technology to be successful. The other one was that the technology has to be feasible, and I want to make a claim that we've shown that the hardware is now feasible. And so there were research prototypes, the machine from HP Labs, and we just saw direct CXL from KAIST, and really making that happen, right? So in terms of research, I think we've shown that technically this is feasible. But there's also, commercially speaking, hardware that is starting to show up or has even showed up, right? So in the RDMA provides partial disaggregation, right? It requires you to access the memory outside using I/O, RDMA I/O, or using a paging mechanism, which is not the same as loads and stores of memory, but it has a lot of properties of disaggregation, good properties. And so the access granularity is a little bit bigger. It's 4 kilobytes minimum, or no, if you're using paging. If you're using RDMA, you can do even like a single byte, but you don't want to do a single byte just because it's very expensive to launch an IO for a single byte. So you want to use maybe hundreds of bytes or maybe thousands of bytes at a time for efficiency. And so that technology has already been deployed, like in the 1990s by InfiniBand. It wasn't commodity, it was used in supercomputers, but in 2010s with Rocky made that possible over Ethernet. And initially directly over Ethernet, and more recently Rocky V2 over IP, and so for commodity systems. And so that technology is already successful, and that provides, I would say, part way through memory disaggregation, not direct memory disaggregation. And in addition to that, we know CXL specs are under its way. And so CXL will allow memory to be accessed via loads and stores, like we saw with direct CXL talk. And 2019, actually, we had the specification for CXL v1. And that is mostly initially motivated for being able to have GPU access CPU memory and CPU access GPU memory inside the box. And so it was not really disaggregated. And more recently, they've been looking into using memory expander cards, but also inside the box, not disaggregated. And that was for CXL v1. And that one, even though the spec was in 2019, we expect the first products to be coming out the beginning of 2023. So that's CXL 1.1. And the delays here have to do with, okay, the entire ecosystem has to support that standard, right? And so not just the memory vendors, but now the CPU vendors have to, and Intel has been promising to have CPUs that support CXL like at the beginning of 2022, and they have been slipping, the current plans, the announced plans are beginning of 2023 to provide the first CPU from Intel that will have CXL supports Sapphire Rapids in the beginning of 2023. And we also have AMD Genoa coming up with CXL support. And yeah, it's a good point that CXL Genoa is on the market. And now that is not disaggregation, but it's a first step towards disaggregation. And so with V2, CXL V2, you have memory pooling, and that is going to make disaggregation more full, but not completely there yet. And in CXL V3, we will allow the cache coherent. And the difference between pooling and cache coherent is that pooling, you have only one party accessing the memory at a time, and then cache coherence, you can have shared memory access to the pool. Now, you can do a little bit of pooling with V1.1, but it's kind of a tough one. It's much better to do this with CXL V2. Okay, so I believe we have feasible technology and we have enough momentum, and the things are going to be coming up next year, like at least for the memory expander cards. And then from there, I think it'll be a small step for us to get memory disaggregation. So this is the trajectory that we have, that I expect for memory disaggregation. And now anybody claiming to predict the future in technology is probably lying. And so that's why I have this slide with very faint gray colors in terms of when this thing is going to show up. Like we know that CXL 1.1 in early 23 is going to be available, but the higher levels of CXL and the disaggregation, I expect that to happen over the next several years. And first with multi-ported CXL, and that means you don't have a fabric. You have a memory module that has multiple CXL ports that you can connect it to. And then you can go to multiple hosts. And it's not going to be a large number, like 2 or 4 hosts you can have. And this is the trajectory that storage disaggregation followed. Like we started with multi-ported disks. And in the same way, I believe that with memory, we're going to start with multi-ported memory. And so that's the first step. And then eventually, and this is, I have a big question about CXL switching and the performance of that. But if that works out, then we'll be able to attach more hosts to the memory, and then we'll have switched CXL, and that will be able to same memory being used within a rack or within a few racks, but not going too far away, because then you have problems of latency and speed of light concerns. And then eventually, I expect the fabric to be converged. And so not having one fabric for memory and one fabric for network, but running CXL over Ethernet IP, right? And by the time, hopefully, the Ethernet latencies will be better, the switching latencies for Ethernet will be closer to what we like switching latencies for CXL to be, and then we'll be able to do this over Ethernet. And so these numbers that I have here for the years, you notice that the ranges started getting broader and broader as we go into the future. And in fact, some of these things may take more than what's over here, right? And this is not research trajection. It is commercial availability that I'm speculating about here. Okay, so Now I'd like to talk about the second lesson that we learned from history, which is, well, the first lesson is that there are some very high barriers and 2 requisites for disaggregation to happen. And so the second lesson is that, okay, once we overcome these barriers, once it happens, it brings about a much bigger impact than you expected. So there's a surprise impact. And I want to talk about the surprise impact of memory disaggregation. And this is where the researchers come in, right? Because a lot of that impact is driven by new research and by trying to do cool new stuff with memory disaggregation. Okay, and so, and I have here a note that I should be wrapping up, and I see us. And so I'm going to go through this and take questions as well. And so there's a lot of topics that are ripe to be explored with disaggregated memory in traditional applications, like key value stores, how to build a better key value store using memory disaggregation. And we have a talk by Sec1 later in this section, who is my co-authors on this work on using RDMA-based disaggregation to build a better key value store. But no, that is also going to be now, that's with RDMA, but with CXL direct attached load and store disaggregated memory, that's also going to be very interesting to see how to build those key value stores. Same for building file systems where you can keep the page cache in disaggregated memory so everybody can use it. Database systems where you're using disaggregated memory for distributed query execution. NoSQL, better data structures for disaggregated memory. I know there's a talk in the next session about using RDMA to build better data structures for databases, but this is also true for NoSQL systems. And streaming analytics, you can think of a system like Kafka running over disaggregated memory, because in streaming analytics, you have to disseminate data. You have to send data everywhere. Well, disaggregated memory is a very good place for you to do this. You put the data in disaggregated memory and everybody can get to it. And machine learning, so you can think about distributed or federated learning where you can keep your model in disaggregated memory instead of a parameter server. And once the model is there, you can have training and you can have inference being used by several different servers, right? And so all of these traditional applications will benefit from disaggregated memory. And there's a lot of research on how to best use this. So I gave a very high level idea and intuition of why it's useful, but there's a lot of work which is needed to make it happen. Like the devil is in the details, and I expect that a lot of work will happen in this space. I would like to, in the next couple of minutes, to speak about a few cool things we have been doing with surprising impacts of disaggregated memory. And one is the notion of a fluid memory, which is the ability to expand memory online and transparently. And that means your application gets more memory, and you do it online without powering off the machine, without quitting the application, without rebooting the machine. The application just gets more memory. And do it transparently without changing your applications, without changing your operating system, and without even running agents in your operating system. And so you just have memory that shows up in the applications, and we're talking about applications today without any changes, without changes to the operating system. And in fact, I don't know exactly how to do this. I think this is an impossible problem to solve, to do it completely transparent. But what we can do is, if we have a hypervisor, which at VMware we do, and we can just change the hypervisor. And so, and the basic idea here is that the hypervisor can map the memory and the disaggregated memory to the guest physical. And then we use suspend and resume functionality in the hypervisor to expose the extra memory. And so we basically, hypervisor tells the operating system, we're suspending you and we're resuming you. And you can do this in 1 second, like you suspend and you resume. And when the operating system resumes, it sees additional memory, and then the application sees the additional memory. And in fact, if you're interested, we have a demo of this running. So we are running an application, which is a system called R, Statistical Processing Memory. And we just upgraded so that R can have more memory we didn't have any changes in R, any changes in Linux. We only had to change the hypervisor. So another thing we can do, and I'm going to wrap up in another couple of minutes, but is being able to migrate VMs instantaneously. And VM migration is one of the most popular features that we have in our hypervisor. Like, our customers really love it. But once VMs start growing bigger and bigger, migration takes longer and longer. And so once you have disaggregated memory, you can do immediate migration, because most of your memory being disaggregated memory means that you just have to copy whatever is in local memory to the destination host. And so migrating the VM doesn't require you to copy everything, because the things that are in disaggregated memory can just be logically attached to the destination targets of the migration. And that becomes super fast, right? And we have prototypes of these things also working today. And the last thing I wanted to talk about, and this is work that's going to appear in ASPOS 2023, is a very different domain of showing what memory disaggregation enables, which is Byzantine fault tolerance, right? And the observation is that data center failures go beyond crashes, and you can have failures there that misbehave. And in fact, there was a HotOS paper by Google that showed that they have this kind of failures all the time. And if you want to tolerate these failures, you need to have something called Byzantine fault tolerance, and which is something that can make and tolerate these failures in a fairly transparent way. It's a technique that allows a service to be fault tolerant against Byzantine failures. And now that typically requires a very large number of replicas, 3F+1, where F is the number of failures you want to tolerate, or expensive crypto like digital signatures. And what we have shown with microBFT is that once you have disaggregated memory, you can do it only 2F+1 replicas, which is the same number of replicas that you need to tolerate crash failures like in Paxos, without using expensive crypto. You can do this with very cheap crypto. And so that means that you can do this at the microsecond latency. And if you're wondering about how that works, now feel free to ask a question. I'll be happy to go into more details and also the performance of this. But basically, we can do Byzantine fault tolerance at the microsecond scale using disaggregated memory. And now I wanted to leave some time for questions, and so I'm going to conclude. And so basically, by summarizing everything I told you today, right? When you look at disaggregation for things that have succeeded, like storage, like power and cooling, like GPUs, we learned two things, right? First of it is that disaggregation succeeds based on two requisites. One of them, it needs to solve a burning problem that affects a large fraction of the industry. And the second is that it needs to be technically feasible. And once these two requisites are met, then disaggregation can happen. And once it happens, there's a high barrier, disaggregation leads to a surprise impact. And I gave a few examples outside of memory disaggregation and some examples of things that we have been doing recently. And I'm happy to talk about more about them. And I expect that most of the surprise is not realized yet. And that's why a workshop like this one is interesting, right? Because we can discuss the research that is going to produce that surprise. And so, and with that, I'm going to stop and take a look at questions and see if there's anything. Let me just check here on Slack. Okay.
Before we get to the Slack questions, is there anybody in the room who would have any questions? This talk.
Okay, is there anything happening in the room I cannot see? Okay, so while we wait for the room, let's take a look.
Oh, hello, hi, Marcus.
Yes?
Yeah, great talk, Ian here. So I have two questions. So one is, as you said, there are like these burning problems, and these are the exact problems for almost all my papers motivation. And there are always people who don't believe in these problems, and there are people believing these problems. But more relevant today, if they're really burning and the technologies are not ready yet, do you think we need some more immediate solution for the burning problems? Like, why are these problems suddenly burning now? And how do we solve them in a more immediate term before these technologies can really happen? And the second question is, one part of the disaggregation that you haven't touched is performance. So I've talked to people with all these benefits, saying, like, what about performance? Like, if my performance, like if my training is going to be slower, I don't care about any other benefits. Do you have any comments on those?
Yeah, which I think has to do with the technical feasibility, right? Because technical feasibility is not a black and white thing. You have to do it well, and that boils down to performance, right? But let me start with the first question now. I suspect that you may be, when it comes to your papers, right, getting a lot of feedback from academia. And now I'm talking about commercial success of disaggregation, and what I'm hearing from people outside of academia and to our customers, right? And they have a memory problem, right? And so those are not the referees of your paper, or people that go to conferences like, or workshops like this one. These are people that are deploying machines in private and public data centers, or these are the hyperscalers. And those people, they're having memory problems. Now, you don't have memory problems everywhere. And so if you're just buying one server and you have a small business, and you might as well just buy half terabyte of memory, and that's okay. A one-time purchase, you could do this over 4 years, amortize it over 4 years, you're okay. If you're a larger customer, you have a medium or large business, then, like I said, memory is becoming more than half of the bill of materials. And if you tell somebody that you can make that cost much lower, then they'll go for it. And so hyperscalers are very excited about things like memory disaggregation. And in the commercial world, I think the story might be a little bit different from what you hear in the academic world. Now, so that's the thing about the burning problem. Now, in terms of performance, you're absolutely right that it needs to go fast. And this is a place where performance is something that gradually gets better. And the numbers that I've been hearing about performance of disaggregated memory with CXL is that it's going to be another 100 nanoseconds for every hop that you have to go. And so once you get out of memory DIMMs over CXL, you have to add 100 nanoseconds. The memory itself is around 100 nanoseconds of access time. If you have to go then to a switch, you may have to add another 100 nanoseconds, and you go from switch to the other host, it's another 100 nanoseconds. So the total, if you add up these numbers, is like 400 nanoseconds ballpark. Now, that is not ideal, right? Because memory this is 4 times bigger than memory. The good news is that once you do this for loads and stores, as opposed to like RDMA, where you have I/O, the entire processor pipeline and the cache prefetching and all that technology can kick in and hide that latency. And so the processor is already designed to deal with latencies that are 100 times bigger than what in the L1 cache, right? So memory is 100 nanoseconds, L1 cache is 1 nanosecond. And so there is technologies inside the processor to hide that memory latency by prefetching stuff in the execution pipeline. And everything applies once things are in a load and store interface. And so even though it's much bigger now, and 100 to 400, still the fact that you can do loads and stores is really helpful for performance, and that gives me hope. Now, the proof is in the pudding. I think once we have real CXL and people start playing with the applications and the latencies there, then we'll see how much slower they are. There was, I believe, a paper from Microsoft that looked into simulating CXL memory to see how much slower applications go. And they didn't have real CXL. They simulated this by creating a NUMA nodes where you put the memory and you don't put any CPUs, you don't assign any CPUs to run your application. And so all your memory access is going over NUMA. How much lower does it go? And they had pretty decent numbers for a large number of applications. Not everything, of course, was running a good speed, but there were a large number of applications that were running quite decently. And so that Microsoft paper had some numbers for you to look at. I think those numbers look very promising. Okay, so let's see. Oh, the other thing about performance is that that's something that also improves gradually over time, right? So once you're past at the point where some applications, important applications, can run fast enough, you adopt the technology, and then the technology improves over time, and then more and more applications can run, right? And I think that's the trajectory that I expect to see with CXL memory. And in a sense, it was a similar trajectory that storage went through when it had to be detached. And like nowadays, you can use just Ethernet to attach your storage, right? It used to be super fast InfiniBand, and before that, like direct SCSI connections. Okay, so there's a bunch of questions in Slack here. So let me see. Hassan is asking for CXL over Ethernet IP. What do you think is the requirements, operation rate, latency, and bandwidth? Okay, CXL over Ethernet. And yeah, so latency, I think it's going to have to be hundreds of nanoseconds still. And just like I mentioned, like 400 nanoseconds. So, and I think Ethernet can't do that very well today, especially if you have to go through many switching, through many levels of switching. And so I expect this to happen first, like within a rack, and then you only have one switch to go around, and then eventually one switching, and also the cost of crossing the various layers, especially in the network adapter, costs a lot of latency as well for Ethernet, and so that needs to get better. But no, hundreds of nanoseconds, maybe 500 nanoseconds would be a good number. So bandwidth is a bigger problem. The good news about network bandwidth is that's been increasing, and so 200 gigabits, people are talking about terabit networks these days, and I think terabit would be pretty good for this thing. So, which means like 100 gigabytes per second, and so that's approaching the kinds of latencies that you see in your bus already. Now, question from me here: how does disaggregated memory allow 2F plus 1 BFT? Okay, yeah. So that was one of the applications that we thought about, and so that's the ASPLUS 2023 paper, and this is the key idea. I didn't go to this because I didn't have time, but basically the soul of a BFT protocol is a mechanism to prevent lying. Like, you don't want the Byzantine party to tell different things to different people, and that's called equivocation. And so, and we use disaggregated memory to prevent equivocation. So how is that? Because with disaggregated memory, we can implement what's called a single writer multi-reader register. So this is a memory location that only one person can write to. And we have different locations with different writers, but only one person can write to. And that prevents you from lying, because once you write to that, everybody can see that, right? And so your memory essentially becomes part of your trusted computing base. And people have shown that if you want to do 2F plus 1 BFT, you need to have some trusted hardware, right? You need to have something that goes beyond, otherwise there's an impossibility proof. And our trusted computing base here is the memory, that the memory is in a different trust domain from the rest of the system. And then we can use this to implement Byzantine fault tolerance. Now, there's another question. I'm not sure how we're going to do about the time here. I have about a minute time left, and let me check with Ian what I should do. Okay, so I'm going to use that. Let's see. There's a question from Zach Blanco. I have a question about your thoughts on CXL architectures and what will be possible to deploy at scale. I think scale will start with a rack. With my current understanding, CXL technologies are built over PCI interconnects. One of your slides mentioned over Ethernet, some research. Yeah, so Ethernet is very far-fetched, and I don't know if it will happen. It was going to start with a rack. Low latency is the main drawback. Stephen is more radical, yes. So I absolutely agree with the lower latency. That's why a rack, I think, is the right place to start with. Okay, Daniel, do you expect, a question from Daniel, do you expect we will have full cache coherence to realize your use cases? Yeah, and so CXL 3.0 is about that. So I think full cache coherence is definitely something people are working on, and I hope that we're going to get full cache coherence. And I expect that it's going to work, but what I doubt is that we'll be able to get two things at the same time, which is we're going to be able to get cache coherence and we're going to be able to get scale at the same time. I doubt this is the case, and so it's going to be like one rack with full cache coherence, or maybe just multi-ported memory, like 4 machines with full cache coherence, but not a large number of machines with cache coherence. Probably unlikely, would be my guess. Okay, I think I should stop this. We are on the hour. So thanks a lot for listening to me. And if you have additional topics of discussion, always open to that. And feel free to reach out and send me an email.